Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to chat with you about the expansion of materials. So first of all, kind of understanding how molecules work, all right? Let's start with that. So in a solid, and I'm just going to make like a one-dimensional example here. These dots that I'm drawing represent different molecules, and imagine that they're connected by springs. Right? And the molecules themselves are constantly moving. Remember, temperature is a measure of molecular kinetic energy. So these molecules are vibrating back and forth. And the higher the temperature, the faster they're vibrating. Well, also, the faster they're vibrating, what happens is the average distance between the molecules increases. And that has the effect of, if I look at this beam, of lengthening the total length of that beam, right? So now, let's ask ourselves, what type of math shall we attach to that? So if I have some sort of object that has a certain length, we'll say in this beam here, we'll say from here to wherever the end of the beam is here, we'll call that L sub O here. The change in length, right, the simplest mathematical formula, if you will, to attach to the change in length is to say that it is directly proportional to the original length and the temperature change. The proportionality constant, right, it's usually written with a letter alpha. That's called the coefficient of linear expansion. I wrote that right here. So that's just a number for any given material that reflects how much it will expand. Now, I don't have any expansion coefficients here to talk about, but it's a number that will have units of 1 over degrees centigrade. Now, in this equation here, the original length can be in anything you want. It can be in feet, inches, miles. The change in length will then come out to those units. Then your temperature here, your delta T, is going to be a difference in centigrade. Now, for surface area type of problems, if I had some sort of object here, right, and we looked at its surface area, if you heat it, all right, and its temperature goes up, what happens is the object will expand in all directions. Now, you can't visually see it, all right? These are very, very small expansions, right? But they are measurable. So you'll have some sort of change in area for this object. And in a similar sense here, we can say that the change in area is directly proportional to the original area and the temperature change. And the proportionality constant is usually called, usually denoted with the Greek letter beta. That's called the coefficient of area expansion. And for a three-dimensional problem, we can say that the change in volume is directly proportional to the original volume and the temperature change. And there's an expansion coefficient for that called the coefficient of volume expansion. All right, so I've written these formulas down here. Now, I'm not going to explain why this is in the video. Maybe I'll talk about this in class, but it's pretty easy to show that, all right, when you have alpha, beta, and this one here, Greek letter rho, right? This one is the coefficient of linear expansion. This one's the coefficient of area expansion. This one is the coefficient of volume expansion. It's pretty easy to show that given alpha for any given material, the beta is approximately 2 times alpha, and the rho, that's supposed to be a Greek letter rho, is approximately 3 times alpha. So for our purposes, if we know a linear coefficient of expansion for any given material, if we double it, we can use it for area problems, and if we triple it, we can use it for volume problems. So that's pretty well all I need to talk about for now on expansion coefficients. I think I'll just end this video here, and I'll make some videos about your homework. Hope that you enjoyed this. Have a great day.